Part of the work I shall talk about this afternoon was done by a PhD student, Ahmed Al-Shahiri, who graduated a couple of years ago. Okay, so what is the Stokes problem? Let's start with a mathematical description of the problem. So we have the mathematical statements of the conservation of momentum and mass with some prescribed dirichlet boundary conditions on the velocity field defined in some nice domain omega with boundary gamma. So that's the Stokes problem. We want to find a solution to this problem in terms of the velocity and the pressure. So the motivation behind this talk is being able to solve discretizations of the Stokes problem and to be able to do so in an efficient and a robust manner. And if we look at discretizing the governing equations using either the finite element or a spectral element approximation, we arrive at systems of equations of the form given by equation 2. So you can think of A as being some sort of discretization to the diffusion operator in the momentum equation, B transpose, the discretization of the gradient operator, and B, by that matter, the divergence operator. You'll see that there is an operator D in the system. For the Stokes problem written in the previous form, so for the Stokes problem written in this form, the operator D, or the matrix D, if you like, is just a zero matrix. So you have a zero block in the bottom right-hand corner. And the various matrices in the system have nice properties. So A being a discretization of the diffusion operator is symmetric and positive definite. And we're interested in operators D that are symmetric, positive, semi-definite. Okay, so the focus would be on solving systems of equations of this form. So why is the Stokes problem important? Well, it's a fundamental problem in fluid mechanics. It describes slow viscous flow, so it's worthy of study in its own right. When you're solving time-dependent Navier-Stokes equations, usually some sort of time-splitting or projection schemes are used for solving those equations, and these involve, first of all, using an explicit scheme for discretizing the convection terms that arise in the equation, and then using some projection scheme where you're looking for a velocity field that satisfies the mass conservation property, and in conjunction with an equation for the pressure. So within a time-splitting approach to the Navier-Stokes equations, we quite often have a Stokes operator to invert, and that can represent the computational overhead in solving the Navier-Stokes equations. And it's the same if you look at an even more complicated system of equations, for example, creeping flows of viscoelastic fluids, which have a nonlinear constitutive law in addition to the conservation laws to solve. And again, the Stokes problem forms a fundamental part of the computational effort that's required to solve those problems. But it also has an intrinsic interest, and this is perhaps where my motivation comes from this afternoon, in being able to study the Stokes problem and looking at some of the properties of iterative methods for solving a system of equations. So let me begin by describing some of the computational difficulties that are associated with solving both the Stokes and the Navier-Stokes equations. The first thing is that there is no evolution equation for the pressure. So if we're looking at time-dependent problems, we have a material derivative that occurs in the momentum equation. The conservation of mass doesn't have a time derivative, and indeed there is no evolution equation for the pressure. And pressure can be viewed, and is, a Lagrange multiplier. A Lagrange multiplier that's in there to ensure that mass is conserved. In the governing equations, pressure only occurs as a gradient term, certainly for incompressible flows. And so you can add any constant onto the pressure and it'll still satisfy the governing equation. So pressure is only determined up to a constant. And in order to obtain a fully determined system, we have to add something. So when solving using, for example, finite difference methods, what's generally done is you impose the pressure at a point, and that is sufficient to remove the indeterminacy in the equations. And when you're solving the Stokes equations on a structured mesh, so just think of a normal Cartesian mesh, you have, if you use central difference approximations for the pressure gradients, the occurrence of what's called a checkerboard mode. So if you think of a checkerboard or chessboard and assign the values +1, -1 alternately to each row and subsequent rows, you can see by taking a central difference approximation of the pressure, that mode will be identically 0. And so this can give rise to oscillations in the numerical approximations. So we need to avoid the onset or the beginning of a checkerboard mode in the pressure. If these do occur, they can cause numerical instabilities, and that, of course, is a disaster. The way in which this is circumvented in finite difference or finite volume type methods is to use a staggered mesh. So to offset the locations on the grid where the velocity components and the pressure are specified. And if you do this, it will avoid this checkerboard mode. For finite elements and spectral element methods, which are based on a weak formulation of the problem, spurious modes can still arise, but we need to use different types of techniques to eliminate or eradicate them. So let's set up the weak formulation then of the Stokes problem. So we define suitable function spaces for the velocity and pressure. So velocity is in H1, the components are in H1, and the pressure is in L2. And typically, to remove the indeterminacy in the pressure, what you do is to insist that the pressure has vanishing mean over the domain, and that, if you like, is an alternative to specifying the pressure at a point. And these spaces then are also discretized by appropriate means. So the question is, how can a vanishing pressure mean be implemented computationally? This is a condition on pressure over the whole domain, and is a little bit tricky to implement, and great care needs to be taken in order to ensure this condition is satisfied. But I will also show in this talk, and perhaps it's the main point of the talk, is that this condition can also lead to advantageous properties when you solve the discrete problem using iterative methods. It's difficult to implement this condition because what you'd ideally like, of course, is for all the basis functions, that you use within a finite element or spectral element method to have this property. And it's not possible to do that in general. So let's look at the weak formulation. So you take the governing equations, typical sort of finite element construction, you multiply by a test function, integrate some terms by parts, and we end up with the variational problem given by this set of equations. And in the weak formulation, there are two bilinear forms, A and B. A has the properties of being continuous and elliptic, and B is continuous, but B must also satisfy a property that is known as the inf supercondition. And this gives you the type of spaces you can use for velocity and pressure. So you can't choose velocity and pressure independently. They have to be chosen to satisfy a compatibility condition. And the mathematical theory for Stokes problem was developed by Bretzi and Babushka. And Babushka died very recently at the grand age of 93, I think, very active until very late in his career. And in fact, he had a renaissance after retiring from the University of Maryland. But I think that renaissance period lasted a period of 20 years or so. He retired not retired, but moved to the University of Texas at Austin, where he spent his latter years. So the theory for the finite element approximation for Stokes problem is very well advanced and understood. Okay, so I want to look at an alternative formulation, and the only difference with the equations I gave right at the start is that I've now modified the mass equation to contain a non-zero right-hand side. And the right-hand side is some parameter lambda, which is at our disposal, times the domain integral of pressure. So why have we done this? Well, if you take the conservation of mass, the second equation there, and integrate it over the domain, using the divergence theorem, you can show that the domain integral of pressure is zero. So you get the vanishing pressure constraint out from this immediately. And as I shall show later on in the talk, this addition, or alternative formulation, has an advantage in terms of the performance of iterative techniques. Okay, so for a number of years, I've been interested in spectral methods, and you can view these as being high-order finite element methods. So let's look at how one constructs the velocity and pressure approximations. So Pn of omega k here will be space of polynomials on omega k. Omega k is like an element or a subdomain, if you like, of some larger domain omega. And these are going to be polynomials of degree less than or equal to n. And then we choose the velocity approximation space to be the intersection with the continuous velocity space and this space of polynomials. So these polynomials in Bn will be continuous across element boundaries because they belong to H1, but the derivative in general will not be continuous across the boundary, although asymptotically we do get continuous first derivatives. And so on each element, we approximate the velocity using Lagrangian interpolants. So the functions I have at the bottom of this slide, the hi of xi, these are polynomials defined on the interval minus 1 to 1 that interpolate the velocity components at the so-called Gauss-Lobato points. So these are non-uniformly spaced points between minus 1 and 1, and they have the special property that they give rise to quadrature numerical integration rules that are as accurate as possible. So if we're using polynomials of degree n, and because we include the endpoints as being nodes in the approximation, the corresponding Gauss-Lobato integration rule will be exact for all polynomials of degree 2n minus 1 or less. So there are very significant advantages in using interpolants based on the Gauss-Lobato points, because using the weak formulation, and the weak formulation involves integrals, and we can get accurate representation of the integrals using Gauss-Sabato quadrature rules. Now, the space for pressure is a little bit different. So here we're using essentially polynomials of degree n-2 or less in each coordinate direction. And we're using, as our nodes for the pressure approximation, the interior Gauss-Sabato points. You may ask yourself, why don't we use the same approximation as velocity? Why don't we just use polynomials of degree n? And the reason is that if you did, you would end up with incompatible discrete spaces. And what I mean by that is that the spaces will not satisfy the discrete equivalence of the inf sup condition that was developed by Babushka and Bretzi, also known as the LBB condition. And so you have to be careful in choosing the approximation spaces for velocity and pressure. Again, if you don't choose them to be compatible, you also end up with spurious pressure modes. And spurious modes within a spectral approximation are more difficult to handle than within a finite difference approximation. These can give rise to wildly fluctuating approximations. So it's important to choose the discrete spaces appropriately. I won't go through the detailed mechanics of forming or discretizing the weak formulation, but if you do, you arise at this following discrete problem. So the first row is just the discretization of the first component of the elemental equation, second row, second component, and the final row is the discretization of the revised mass equation. So this is the system of equations that we want to solve. It's a nice structure, it's symmetric. Let's say the matrix A is symmetric positive definite, and the matrix A, of course, is the stiffness matrix of either the finite element or the spectral element discretization. The C transpose matrices here are the discretization of the gradient terms, and B arises from the integral of the pressure. So this is the system of equations we want to solve, and we want to be able to solve this efficiently. And in particular, to look at whether by choosing the value of lambda, we can do something clever. Okay, so I've rewritten that system in the form Kx is equal to P. So K is just that big matrix I had on the previous slide. Because of the structure of this system of equations, conjugate gradient, or one of its variants, is an obvious choice, obvious candidate as a method of solution. And the rate of convergence of CG type methods depends both on the number of distinct eigenvalues of K and also on the ratio of the largest to the smallest eigenvalues. So we'll bear that in mind. We can come up with a more efficient solution technique by using a preconditioner. So if I take a preconditioner P and multiply both sides of the discrete problem by P inverse, then by suitably choosing P, we can reduce the number of iterations required for convergence. So the question is, how should we choose P? Well, first of all, there are the two extreme cases. So P equals I, the identity, of course, not using a preconditioner, just solving the original system, which is very expensive. You could choose P to PK, but of course, that's just inverting the original matrix. So we want to try and find somewhere in between I and K that is able to lead to a system that is easy to solve and is a good approximation to the original system.
Sorry, why don't you just invent K, direct method, Gaussian elimination?
Because in many instances, if you're solving problems in 3D, I'm using spectral methods. It's a full matrix. It's a lot of storage. So let's look at block diagonal preconditioners. So choosing P to be of this form, and we'll look at choices for P1 and P2 will turn out to be the same. Choices for P1, P2, and T. So, as I say, the performance of conjugate gradient depends on the eigenvalues of the system. So, can we find the eigenvalues of this problem, which is the same as this generalized eigenproblem, k minus mu p x is equal to 0. Okay, so just rearranging that equation, we get the following. We want to find the values of mu. Now, in the special case where you're dealing with the finite element approximation, and b is equal to 0, and if you choose P1 and P2 to be the finite element stiffness matrices, and T to be the shear complement, then Ellman, Sylvester, and Watson have shown that there are precisely 3 distinct eigenvalues. So if you were able to perform exact arithmetic, conjugate gradient would converge in 3 iterations. That, of course, is not possible. We can't perform exact arithmetic, and in fact, the ability to construct the shear complements is tricky, and it is a full matrix. So even if you were able to do this, it would be very expensive. Okay, so let's turn now to the more general case, so where b is not equal to 0, and we choose again P1 and P2 to be either the finite element stiffness matrix or the stiffness matrix associated with the spectral element method, and we'll take T to be the pressure mass matrix. And so let's consider a block diagonal preconditioner of this form. So again, we're interested in the eigenvalues of the preconditioned system. Before I show you some results on the eigenvalues, just an illustration here showing the spectral convergence. So here we're just solving a problem on a square. I think the square has been decomposed into 6 spectral elements. Solution, so a problem with an exact solution, and we obtain the normal convergence properties associated with spectral methods. So if you're approximating either a function or the solution of a PDE that is smooth, the spectral approximations converge faster than algebraic. Okay, so faster than any finite power of 1 upon n. Okay, so let me just go back. So now I'm going to look at how one can choose the value of lambda to perhaps optimize the performance of the preconditioned conjugate gradient method. Okay, so this first set of results is showing the influence of lambda on the condition number of the preconditioned system. And on this graph, we see 3 different values of n, 8, 10, and 12. And looking at the variation of the condition number of this preconditioned system as a function of lambda. And the interesting thing from my point of view is that there is a sort of a plateau region in terms of values of lambda, which give an almost constant value of the condition number. And so this represents a location, perhaps, of the value of lambda for which one can search for an optimal preconditioner of the block type. yeah, so this is looking at just 3 different values of lambda and looking at the behavior of the condition number. Again, you see here for the 3 values have been considered 0.1, 0.5, and 10. Condition number grows slowly with n, so it doesn't give rise, for these values lambda didn't give rise to an optimal preconditioner. And what I mean by that is a preconditioner that leads to a constant condition number, which in turn would lead to the same number of iterations being required for convergence, independent of n. Now, if you take a small value of lambda, this is the value of lambda as 10 to the minus 3, we see that, in fact, the condition number decreases slightly. There's a very exaggerated scale in the vertical axis here, but a very slight decrease in the condition number. So this perhaps hints at there being an optimal choice of lambda for this particular block preconditioner. Just leave that and show you a table of values. So here we're looking at different values of lambda. Remember, lambda is the parameter that multiplies the domain convergence of the pressure that occurs on the right-hand side of the conservation of mass. N is the order of the spectral approximation. And this gives the number of preconditioned conjugate gradient iterations to reach convergence for this parameter range. And what you notice here is that there is very little variation in terms of the number of iterations. And indeed, if we look at some higher values of lambda, larger values of lambda, again, we're looking at between 35 and 50 iterations to converge across spectral values of the approximation space. And if we were now just to fine-grain the values of lambda that we searched, there is, for this particular problem, a value of lambda which gives a constant condition number, irrespective of the choice of n, and that's given by the value associated with the pink curve. Okay, it's quite precise. But the important thing is that for values of lambda away from this value, there is very, very minor variation of the condition number with this parameter lambda. Okay, so I think I need to show that. Oh, of course I do. Yes, so this is looking at the rather than condition number, the ratio of the largest to smallest eigenvalue, and you can see that in the case of the optimum value, the condition number is reaching a plateau, and these ideas can be extended to problems in more complex domains. This is an example of a flow through a contraction geometry, just to illustrate that we're not confined to solving problems on rectangular regions. And I think I'll just end with some conclusions and leave plenty of time for questions. So what I've done is to present an alternative formulation of the Stokes problem, essentially by adding a term to the right-hand side of the conservation of mass. And that has the advantage of removing the indeterminacy of pressure, but also has advantages in terms of designing robust iterative methods for solving discrete systems. We looked at a number of block preconditioners for the spectral element discretization. Apart from using the spectral element stiffness matrix, we've also looked at the finite element stiffness matrix within the preconditioner. That has, as you'd expect, a worse performance, not significantly worse, but doesn't perform as well as the spectral element preconditioners. What I've shown is that by suitably choosing the value of lambda, although it's not restricted to one particular value of lambda, you can obtain enhanced performance of the preconditioners and the iterative solvers that you use to solve Stokes-like problems. And this will have the advantage of not only removing indeterminacy pressure, but having an iterative method that is independent of the size or the order of the approximation. We've seen that there is a value of lambda which does lead to an optimal preconditioner, but we've also shown that if you choose lambda within a reasonable neighborhood of that critical value, if you like, then there is not a significant deterioration in the performance of the iterative methods. And shown that the spectral method is applicable to problems in more complicated geometries. The last thing I want to say is that I'm currently looking at whether it's possible to be able to determine this value of lambda, or the optimal value of lambda, analytically. So most of my work post admin heavy is looking at theoretical issues such as this. And with that, I'll stop and be happy to answer any questions.
Thank you very much.
So have you applied it to other problems, to more problems? I think it's good to validate more the method by applying it to a variety of
Yes,
problems.
so I mean, we've looked at just the model problem of a square and this problem defining the contraction geometry. We haven't looked at extension to other sorts of problems, but I think it's working pretty well. But of course, it needs to be done.
No, but it's just to make it bring it to life.
Yes, yes.
I just want to elaborate on Angela's question because I was thinking the same. So it's either the geometry. So do you have any predictions on what kind of geometries will still fall beyond the contraction one?
I think the general iterative methods can be applied to problems in any geometry. So I don't think it's dependent on that. What could be dependent is the value. So we've only looked at these two problems because there's quite a wide range of values of lambda that give near optimal performance. It didn't vary significantly between the two, but clearly it may not.
You may not preserve that.
Yeah.
If you want.
I had some very naive problems, questions if you don't mind. So a lot of physical problems do have a boundary condition for pressure in them that you wouldn't probably want integral to vanish across the
No. So for those problems, you wouldn't need to.
You wouldn't need to do this preconditioning. Right. Then the other one, it seems that the problem is grad P is undefined, but grad P is always quite well specified. If you don't have one of those boundary conditions for P that rescues you in that way, could you not just have grad P as a generic function and that you don't have to have that indeterminacy from the start?
So yeah, so you'd replace grad P by another unknown. That's possible. I don't think anyone has studied that mathematically. So whether or not that's a well-posed problem.
Yeah, just like a source term with no pressure gradient. Cool. Anyway, interesting to explore. Cool. If we have no more questions, we thank Tim again.
Yeah.